Okay, hi everyone. Welcome to our fourth and final lecture today with my fourth and not final voice. I'm still hoping once I get back to Israel, my voice returns to its normal self. And I'll be honest, I can't tell you exactly what our outline is for today because it's going to be a little hard for me to estimate sort of the pace at which we're going to go. We're going to see how things evolve. I have a bunch of stuff hidden behind the board. Depending on what we end up doing, we'll be able to sort of lift the board and have some elements of surprise going on. But roughly, what I do hope that we'll be able to cover today, we're going to finish talking about dark sectors. Okay, and in particular, what we're going to work through now together is the 3 to 2 case, which is perhaps kind of the most exotic type of interaction out of the ones that we've been discussing. We'll talk a little bit about signals of these things. Possibly, these are all possibilities, a little bit about constraints. And I'm hopeful that we're going to talk a little bit about detection. So that's sort of my hope for us today. Okay? So I remind you, we moved on from talking about mechanisms for studying the relic abundance of dark matter to talking about dark sectors or sort of models, theories that will populate these types of mechanisms. Okay? And so as I said, what I'm going to start with, so this is still in the context of dark sectors, let's talk a little bit about 3 to 2 interactions, because in a way these are sort of the most sort of exotic out of the ones that we've been talking about. They're a little less familiar than ordinary 2 to 2 interactions. But as I want to show you, and I've sort of already said this, it actually happens in the standard model itself. Okay? Ignore what you may or may not be seeing appearing down there. Okay, great. So let's do a little reminder of what happens in QCD. Okay? Okay. So QCD, and I'm caring about a particular part of QCD. QCD is, of course, an SU3 gauge theory. And let me look at the light flavors. Okay, so I have 3 light flavors. Right, this is my up, my down, and my strange. And this theory has an SU3 left cross SU3 right global symmetry. Okay? And then as we flow to low energies, our theory confines. Chiral symmetry breaking occurs. And what happens is that this SU3 left cross SU3, sorry, these are meant to be 3s, SU3 left cross SU3 right, breaks down into a diagonal subgroup. Now in QCD itself, in the standard model, these are of course not exact symmetries. They're only approximate because the masses for these quarks are not degenerate. Okay? So in the standard model, these symmetries are only approximate. Okay? And this theory has, we have 8 broken generators. And so I have 8 pseudo-Nambu Goldstone bosons. Pseudo-Nambu Goldstone bosons. And these are, of course, the kaons, the pions, and the eta. Okay? And this theory of QCD has direct 5-point interactions. Okay? And this happens because we have annihilations where 2 kaons annihilate into 3 pions. Okay? And the way that this happens in the context of the standard model is through a topological term that's called, it's a topological term in the Lagrangian, that's called the Wess-Zumino-Witten term. Okay, and this was a term proposed in actually 2 sets of papers. There's Wess and Zumino. Okay, I realize you guys might not show up in the recording, but 2 beautiful references to read. One is a paper by Wess and Zumino dating back to 71, and the other one is a set of 2 papers by Witten, okay, Witten times 2, in 1983. Okay, so 2 papers by Witten, not 2 Wittens writing the paper. So this is a really By the way, these papers are really beautiful. I really recommend reading these. Really recommend reading these papers. But if you would take this term, and we're going to write it out explicitly in a moment, okay? But if you take this term within the standard model and compute what is the rate for these 5-point interactions, you'd find that it is just right to be a simp if the mass of the involved particles was 100 MeV. Okay? If you calculate the rate, you find that it's just right to be a simp if the masses involved are of order 100 MeV. Okay, so that's a very kind of inspiring or sort of something that would probably push you to think in this direction. And so inspired by this, let's look at QCD-like theories. Okay. Inspired by this, let's look at these QCD-like theories that I've been talking about, okay? So let's imagine the following. Let me do the example kind of similar to this. We'll see we can actually do it much more general than this. But imagine that I have some SUN gauge theory, okay, with some number NF of flavors of degenerate mass. Flavors with degenerate mass, okay? You see I'm already giving them a degenerate mass because this is a way I'm going to be able to ensure that actually my residual symmetry is no longer going to be an approximate symmetry, but actually be an exact symmetry. Okay, so this is gonna stabilize our particles through an exact residual symmetry. Okay, so I have this gauge theory with NF flavors of degenerate mass, and if you'd write down the Lagrangian for this, much like in QCD itself, you'll see that you have an SUN left cross SUN right global symmetry. Okay, and then chiral symmetry breaking occurs. And what happens is that this global symmetry breaks down to a diagonal SUN. Okay, so chiral symmetry breaking occurs, and this theory is now broken to an SUN diagonal. So these should all be NFs. I apologize. NFs. Okay, the symmetry is amongst our flavors. Okay, and this is now an exact symmetry, thanks to this degenerate mass that I've written down for my quarks. And this theory is going to have, depending on the number of flavors, and of course it's on the particular gauge group that we've written down, but there's some general number which we can easily compute how many generators are broken. We're going to have some number n pi, I'll call them, of pseudo-Nambu Goldstone bosons. And these are the guys that I'm going to collectively call my pions. And these guys can be my dark matter. Okay? And this theory, as we've written it down, has 5-point interactions through this Wess-Omino-Witten term. And here's what that Lagrangian looks like. The Lagrangian for this Wess-Omino-Witten term has a very particular form, 2 times n, this is like the number of colors, nc, okay, divided by 15 pi squared. There's an f pi to the 5th. This f pi is the pion decay constant. Okay, so this is my pion decay constant. It has an epsilon mu nu rho sigma. And then it has a trace of all of these pion matrices where pi is pi a times ta, the broken generators. And it looks the following. It's pi, d mu pi, d nu pi, d rho pi, d sigma pi. Okay? What's that? This over here, this is chiral symmetry breaking. Sorry, shorthand for chiral symmetry breaking occurs.
So it's just SUNF.
It's these two that are broken to the diagonal subgroup. Okay, just like in QCD. Yeah.
Sorry, I think I just missed something in the introduction. I thought that the standard model shows us that if we calculate the rate, that we get the right thing to be a sim. So why do we have to insist on the exact symmetry here? We could use the approximate.
Well, my problem in the standard, what I've literally told you here is that if my pions were stable in the standard model, which unfortunately they are not, they could have been a simp dark matter candidate. Okay? I want to ensure stability. So I can choose to write down a degenerate mass term. Yeah.
Do you still get pion mass with the exact
Yes, the pion mass is proportional to the quark mass. So you end up with, that's exactly the thing that we end up with when you look at your Lagrangian in the broken phase. You're going to end up with, your theory has an exact symmetry, including the you definitely have stable, massive dark matter. Okay?
Another question?
Yeah.
The fact that you write an F here is just to give you more possibilities and not because you want to look at the large end.
No. What I'm going to show you here, we're going to talk about, I'm going to show you, and the thing that we're doing here, I'm just writing it in the SU version because it's just so analogous to QCD, but you can do this, so you can do this for an SO gauge theory, an SU gauge theory, an SP gauge theory, provided you have enough colors and enough flavors, which enough flavors is 2 or 3 or more, so it's like a super minimal requirement. This is what happens, okay? The topological term is met, and you have a Wessel-Witten term, okay? So let's just take a look at what we have over here. You see I have interactions between 5 pions, and they're contracted in a very particular way, okay? But these are a 5 pion, okay? 5 pions that are interacting in a very particular way. And as I just said, we can do this not just for this, SUN gauge theory, but in principle, you can do something very similar. So we can do this for any, it could be an SU N gauge theory or an SO N gauge theory or an SPN gauge theory. And in each of these theories, provided I have enough flavors, so in this case, it's NF2 or more. Over here, it's NF3 or more. Okay? But provided I have a very minimal requirement of how many flavors are in my theory, the Wessel-Witten term exists. This is what it looks like. And we have 5-point interactions in these theories. Okay, so what we've gotten from this is, these are all now dark pions. Okay? And so what I've just shown you is that getting 5-point interactions, which would give us simp dark matter, is something completely generic in theory land. Okay? These are generic in QCD-like theories, okay, or in QCD-like dark sectors. Okay? And what you can do is you take, so what do I do in principle? Yeah, is there a question there?
Yeah, just like 3 times the degree versus the lesson.
You don't see it in you write it down in your broken phase, okay? It's a term that has to do with the 5th homotopy group of the pattern of the breaking. Okay, so this is something that appears in your broken phase. Okay, I really recommend the 2 Witten papers, like beautiful, beautiful papers explaining this. Yeah. Okay, so what's the value of having? I have a Lagrangian like this. I see that I have 5-point interactions. Just 1 second. See, I have 5-point interactions, and the reason that we wanted to have these models and the reason that it was still worthy that we did the exercise with the mechanism level is because, remember what we said in principle, I have a theory. What I do is I take the parameters of my theory, and now I literally compute the rate, and I can kind of map that on, right? So what I mean by that, for instance, over here, is that you'll take the parameters of this theory, and you'll compute what is the size of that thermally average 3 to 2 cross section. So what is sigma v squared 3 to 2? In this case, and you compute it, and it's very annoying to compute it because of all the combinatorial factors. But the answer is 5 square root 5, 2 pi to the 5th, number of colors squared over x freeze out squared, mass of the pion to the 5th over the k constant of the pion to the 10th, times some combinatorial factor, I'll call it for historical reasons, t squared over number of pions cubed. Okay? For this piece over here, this is just combinatorics. Okay? Actually, let me just give you a good reference for this in general. So the set of papers in which we sort of work this out, this is a paper where a few authors over here. This was a really nice PRL in 1411.3727. So this is a paper that's called, instead of the simp miracle, it's the simplest miracle. It's the simplest realization we could find for these theories. And another one, which will be relevant soon, is with Kuflik and Moriyama. a 1512.07917 paper. Okay? So just some references if you want to, for instance, dig up this very messy combinatorics. Just 1 second, okay, guys? So you see I have a cross-section, okay, and it has a very particular form, but you see the essence is that now basically I translate what we previously called alpha effective cubed over mass to the fifth, right? Now I can translate what's the relationship, what's alpha effective in terms of my my parameters here. So for instance, over here you'd get basically that alpha effective is some number that I don't care about, but you see that it's really scaling like mass of pion over decay constant to the 10 over third power. Okay, but it's just this is our ability to do a translation, and what that means is if we know that this is there's a particular size for this cross section such that we've obtained our relic abundance. Now instead of drawing some alpha versus m curve, what I do is I draw it in terms of the actual parameters of my theory. So this will look, let's say m pi over f pi as a function of the mass of the pion, and let's say in GeV units. Sorry, that does not look like a GeV. In GeV units. What it just means is that I have some curve that tells me where the relic abundance is obtained. A curve, I don't know, looks something like this. Okay? Let's see, over here goes up to a GeV. Down here, let's say down to 10 MeV. And this theory, of course, you have to worry about when do I go non-perturbative. Roughly speaking, you can kind of think of that's going to set some limit of how large can I go in terms of m pi over f pi, roughly of order 2 pi. Okay? So that's going to combine, give me some upper limit on how high can I take the mass of this dark matter candidate such that I know what I'm actually doing. Okay? But this curve over here that I've just drawn, this is really just that solution to the Boltzmann equation. Or, that which is the more accurate thing of the hand waving that we've done together yesterday. Okay, is there still a question here? Yeah. Yeah, well, you see that so when you work it out over there, you see that you sometimes get a time component. That's why you're actually getting also temperatures appearing in there. Yeah, but that's as I'm saying. In this case, it's contracting in a very particular way. It doesn't mean that every single 5-point interaction that you would write down necessarily gives you the exact same scaling. That's why it's great once you have a particular model, you figure out what happens over here. It could have been that this would sort of point to something very different. It happens to be that it doesn't.
Is there a way to constrain the scale at which the symmetry is broken?
To constrain, depends what you mean by to constrain the scale at which the symmetry is broken. This story as we put it here together tells me that I really am looking at sort of sub-GeV, let's say GeV-ish masses at most. How large are you allowed to take this is kind of related to where is my what is my scale of chiral symmetry breaking? Okay, so up to factors of square root n's and 2's, roughly 4 pi or 2 pi. And that kind of sets the scale for you. See, everything is really looking very like QCD-like scale. That sort of keeps coming out. And I can tell you, I don't have any proof of this, but so far in any attempt that we have made with our model building to try to push these boundaries, for reasons we don't yet understand, keep on getting pushed back to this scale. So, so we really keep on going back to the strong scale for reasons that I don't necessarily think have to be true, or I haven't figured out yet why that keeps happening.
And that's again because of the non-perturbativity?
Well, in this case, it's the non-perturbativity that's setting a lower limit. We're going to talk in a few minutes about how we get, it's putting an upper limit on my mass. In principle, right now, you could think that it could go very, very low. We're going to talk about why there are other constraints that force me to really also have a lower limit. And then combined, they really have a range of masses in which everything is viable. Yeah? And pig over the general mass, I said that this is going to give me a residual symmetry that's an exact symmetry. And that means that my dark matter is literally stable. Okay, I have an exact symmetry that's protecting it. Yeah?
Can you repeat what is the numerator of the combinatorial?
What is the numerator of the, this is just a really, really ugly function that's a function of NF. And per gauge group can compute what it is, and we have a very ugly table, which took a really long time to compute that's sitting in the appendix of this paper. Okay? Okay. Okay, so this is an example, and it's a very general example that holds for all of these classes of theories. We get this simple like dark matter, and then we can go ahead and sort of map out what does this tells us in terms of the parameter space. Now, if you remember, ignore what you're seeing over there behind curtain number 1. If you recall, when we talked about SIMS, we talked about the fact that I need to have 2 knobs, right? It's not actually just enough for me to have 3 to 2 interactions, but I also need to have some way to sort of mediate interactions or shed my heat into light-abundant species. And so just to give you a sense of this, just one particular way in which you could do this in this case. And the reason I think it's really interesting is also just because it's not just that these types of constructions are very generic in theory land, they're also very predictive. Okay, and that's a great thing. If we can show something as generic and also gives us predictions, that's pretty much most of what we want in life in this context. So these types of constructions are also very, very predictive. Just before I say that, let me just mention, I want to bring down the board. Let me just mention that there are other ways that you could do in these theories that you could do 3 to 2 interactions, okay? I've given you the example through using the pseudonumber Goldstone bosons, but there's also been interesting work about how you could do 3 to 2, for instance, using glue balls. So I'll just give you guys some of the references. So one of the references is that Carlson, Hall, and Maciekek paper that I talked about, that original Cannibal paper in '92. They actually start off with talking about glue balls. There's a really nice paper by Sony and Zhang from 2016. This does this, as well as a paper from Lindsay Forstall et al. From 2017. Okay, so just I'm by no means saying that pions are the only way that you could go. There's a lot of other work, even within these theories, about what are other methods in which you could also easily accomplish these types of interactions.
Are those standard model pupils?
What's that?
Are those standard model pupils?
No, not standard model pupils, but using these types of QCD-like theories. Yeah. Okay, so going back to the fact that these theories are also predictive, so let me just give you an example. Okay, so imagine that I look at a QCD-like theory, one of these, okay, any of these gauge groups, and I also have times one of those dark ENMs, okay, one of a dark U1. And just as a side note, and in the second paper that I wrote up here, you can see exactly how you do this. It's very easy to, if you think of this symmetry structure that we had over here, this exact symmetry structure, it's very easy to embed, to gauge a U1 subcomponent such that I still have stability. Everything still works out very well. So it's not even as if it's like another piece you're tacking on. It can actually literally be included in this original theory as we've written it down. But what I just mean over here is, so now I've added the fact that I have some dark photon. So I'm going to call this dark photon. I don't know, here's my ordinary photon. And it's mixing, again, through some size of kinetic mixing to be some dark photon, which I'll call V. Okay, and I'm not going to go into too much detail about this, but let me just show you a plot, okay, or draw a plot more accurately. So imagine, and let me just, for instance, let me fix my gauge group and fix my mass of my dark matter. Okay, so I'm just sort of slicing my parameter space in a particular way. And just to show you, if I think of the relative size between epsilon and the mass of that dark photon, then this is sort of the equivalent to remember when we talked about SIMS yesterday, we had this like epsilon min and epsilon max, okay? So we can kind of draw equivalent curves now in this particular theory. What is sort of the range of validity for SIMS? And you find something that looks roughly like this. So it's a curve that dips down. This is the curve where 2 to 2, where you have 2 pions going to 2 standard model particles. Okay, so this is sort of the WIMP-like curve. There's another curve down here which gives you thermalization. So basically, you can kind of think of it, let's see if I have another color here, just a second. This blue is the best. Thank you, Sarah. Okay, so this roughly would be a curve where I'd have a WIMP dark matter candidate. Along this curve, I'd have an elder. And in between these two is where I have SIMS. Okay? But this parameter space is even more broad. So down here, I'd have a candidate that's not thermalized. Okay? A viable type of candidate that one can work through. There's a region over here, so this here goes down at twice the dark matter mass. And in this region over here, something called semi-annihilations, which we drew, which actually come from the gauged Wessel-Witten term in this theory. So semi-annihilations would contribute. What I want you to take away from this is not so much where these different curves are sitting, but the fact that in this very, very simple construction, different regions of the parameter space just give me different mechanisms for dark matter. Okay? Yeah. So I can either assume that I have a dark Higgs or a Koch-Tuchel bucket. Okay. So I'm not going to go really into much more detail in this type of parameter space and talking about this because I think this is going to be the subject of a whole set of lectures in either week 3 or 4 by Philip. So stay tuned for that. But when he's going to be showing you guys different constraints, this is sort of a type of parameter space. Kinetic coupling as a function of choose is it dark matter mass or is it dark photon mass, and assuming all sorts of relationships, all sorts of really, really interesting experiments that place constraints on this parameter space. When you're going through that, think of this picture, okay? Different regions that I'm constraining, different regions that can be probed, they all have their own interesting dark matter model that could populate it, okay? And yeah, maybe just for completion, I'll just say, that there are, and I'm not going to go through this in detail, but there are so many different constraints that one could draw on this parameter space. If these were roughly those curves that I just drew, okay? So sort of as a ballpark for you guys to take, for most, there's so many different experiments, and I'm not going to go over them, but roughly, sort of, you can kind of think of that epsilon has to be kind of smaller than 10 to the minus 2 to 10 to the minus 3 over a very broad range of masses. There are all sorts of new experiments that are pushing deep down this way and deep down that way, which you're going to be hearing more about. What's that?
Right after Elder.
This one, thermalize. Thermalize, yeah. That's the curve of thermalization. Okay? Okay. One other thing that I'm not going to, I have too many things I want to tell you guys, and I think I'm not going to mention this, so I'm just going to give you guys an interesting reference, so I'm going to add it over here. As I've drawn this over here on this parameter space, this is something that people talk a lot about how we're going to detect these dark photons, what kind of constraints or discovery we can have in this context. But I want to say something more. It's also related to something somebody asked yesterday after class, and that's that you can actually hope to do even better, okay? Not just to say, oh, how can I detect the dark photon, which is giving me a portal between my dark matter and the standard model. But you can actually even hope to actually perform spectroscopy to measure the spectrum of the dark states themselves. Okay, so I'm not going to have time to go into that, but I want to give you guys spectroscopy, or dark spectroscopy, just to give you guys a reference for this. And it really also just completely takes inspiration from QCD. This is a set of papers that we wrote. The first one is 1512. We started off over there, 1512.07.91.7, and a shorter paper, 1706.05008. This one's a very easy read, and hopefully you'll be able to understand what I mean. Is that literally you'd be able to one day measure, be able to see these bumps in a spectrum that you're measuring at a low energy machine, and literally be able to decipher what are the masses of states of your dark sector. Okay? Okay. So, okay. Looks like I will have time. Yay. Okay, so the next thing that I normally would have been discussing, but we're not going to be discussing in detail, are sort of general constraints on dark matter. Let's see. I think when I was little, there was like this show, The Price is Right, and like you open up a curtain, you don't know what's going to happen. I think I opened up. No, it's the wrong curtain. Hold on. Close your eyes. Abort. Abort. Okay. Ta-da-da. Voila. Okay. So this stuff, I'm just going to mention right now briefly. That's why I've also written it down. Don't worry about it. This stuff I do believe you're going to be covering in detail in Ben's lecture next week. But I do want to sort of point out there's some general constraints about masses, just because it's also kind of come up already. So fuzzy dark matter, this concept that dark matter has to fit into objects that we see. So that tells me something about its wavelength needing to be, be able to be contained in certain sizes. That's what we're setting sort of a minimal mass in general on dark matter. But there were two numbers that have already come up when we've been talking together. The first is KeV and the second is MEV. So without going into too much detail, I'll just say there are two sources where that number, mass of dark matter, should be above KeV, stem from. One is just a statement about phase space packing. So if I have fermion dark matter, there's a limit to how many I can stuff into. Right? Fermions don't like to be with each other, so there's a limit to how many I can pack into certain sized objects. And that gives me a bound on fermionic dark matter that has to be with mass above a keV. Okay? So that does hold for fermions. As a side note, if I'm assuming I have a subcomponent that's smaller than 10%, you can easily evade this. Okay? The second one is what's called the warm dark matter limit. And this is just the statement that, if I have dark matter, in principle, it can sort of wash out structure. And so given that we see structure of certain sizes, that tells me some information about sort of the free streaming length. And that combined will give me a bound that's also of the size of keV. And this does hold also for bosons. It applies to thermal relics, to freeze-in, freeze-out and decays. Importantly, it doesn't apply to bosons that are produced at rest. So if you guys were talking about sort of dark photon dark matter and axion dark matter, perhaps in Peter's course or later on in Matt Reese's course, these are ways to get around this. But I did just want to sort of mention, so when we were talking together, and I kind of, when I wrote down what's the mass range in general for WIMPs, what's the mass range in general for some of these particles, and I was sort of writing keV and above, this is the reason that keV kind of came in. Okay? Another number that came up very often was, well, actually not so often. So let me just mention this. And again, this is something that I'm not going to have time to do in detail, but you guys will see this in detail. So right now I'm just giving you the bottom line answer. And you'll hopefully understand why this is the bottom line answer. But basically, constraints from measurements that we have from the effective numbers of degrees of freedom, it sets limits on what masses we could have for particles that are in thermal contact. There are two relevant scales in that context. There's BBN, which happens at temperatures of around an MeV, and cosmic microwave background, which is roughly temperature of EV. Okay, and when you work through all of these things, and there's even, in principle, over the next decade, we're going to see hopefully an improvement by even an order of magnitude on the size of these constraints. But roughly, what this tells you is that if you have a relic that is kinetically coupled, okay, so thermally coupled to the standard model bath at MeV temperatures, its mass should be above an MeV. Okay? And out of all of the ones that we've mentioned, certainly that was one of our requirements that we had, at least on this naive version that I've discussed of SIMPs. Okay? So that means that when I'm thinking of, how low can I go in this mass range for SIMPs? So we've seen over here, for instance, that perturbativity will often sort of chop me off at high masses. But at the very least, I would expect to have a similar type of chop off at an MeV scale dark matter mass, because if I was going beneath that, I'd run into trouble from N effective. Okay? Okay. Okay, and then the last constraint that I want to mention in this context, let's see where I want to mention it. Yes, is this. Okay, so self-scattering. We're going to talk a little bit more detail about this one. So we also have constraints that come from self-scattering of dark matter. And as we mentioned, yeah?
Is there any reason we expect dark matter to be fully properly perturbative in all regimes?
No, it just means, though, that once I've hit a perturbative regime, I don't trust my computation. So where does this curve continue? It doesn't mean that dark matter can't be above here. It means that my ability to trust my computation and to trust my predictions has to be augmented.
So if dark matter was, are we theorizing about it in some other way?
Well, you can try to do all sorts of stuff in a strongly coupled regime, maybe on the lattice, and that's, I think, something that, I know some people who are interested about that, but my ability to, it just means that I'm starting to get corrections that I haven't accounted for that are as important as the ones that I have taken care of. I can't say if people are doing it. I can tell you that people a couple of years back were interested in doing it. Whether or not that's something that's been happening is something that I can't say. I certainly haven't seen yet results going above this regime come out yet in the context of dark matter. Okay, so going back to this last constraint that I wanted to mention. Remember in our first lecture together, we sort of had this laundry list of things that we know and don't know about dark matter. And one of the things that we said is that dark matter shouldn't interact too strongly with itself because this distorts dynamics in dark matter halos. Okay? And so basically, thinking of these sort of self-scatterings of dark matter, these sort of 2-to-2 self-scatterings of dark matter, okay, roughly tells us that there's some constraint on the size of the, it's usually phrased in this way, cross-section of this self-scattering over mass should be smaller than roughly a centimeter squared per gram. Okay? What is this number? If it's 0.1 or 10, there's also some velocity dependence going on here. But sort of as a ballpark, this is a good number to sort of keep in mind when you're working on these types of things. And this is really coming from, from bullet cluster and from halo shapes. But I'll also add that there's some interesting puzzles that are related to these related to this type of cross-section. These are puzzles in structure formation, sort of typically go under the name of core versus cusp and too big to fail, if you've heard of these things. And I do think you guys are going to be delving into this in more detail in later lectures with other speakers. But I'll just say that in principle, there might be some puzzles that are possibly things that are not understood in terms of structure formation. It's possible that these things are totally resolved by astrophysics, but it's also possible that basically that if you have a cross section that's of order this bound, that could also assist with these puzzles. Okay, and the reason that I'm mentioning any of this is twofold. One is I have over here a bound, regardless of what I think about these puzzles. I have here a bound on how strongly dark matter could self-interact with itself. Okay, and if you just think about our SIMP constructions that we've done together, we're talking about strongly self-interacting particles, right? And so the generic expectation would be that if I have some theory that admits strong 3-to-2 interactions, I'd expect to have also unsuppressed 2-to-2 interactions, okay? And once I have a particular theory that I write down, for instance, these QCD-like theories, I can go ahead and literally compute what is the size of my 2-to-2 self-scattering, and then make sure that I'm obeying this bound, okay? And so for instance, if I go ahead and do that over here, okay, so remember we had a 3-to-2 cross-section, and here's my solution to the Boltzmann equation. And I can ask myself, well, what happens if along this solution to the Boltzmann equation, I now draw what is my curve for 2-to-2 self-scatterings, okay? So let me, I'm sorry, it's gonna hide curtain number 2, but I think it's okay. Okay, so actually let me just write out one more thing over here, okay? So these different puzzles tells us that it's also okay, it's kind of also okay if the size of this self-scattering cross-section over mass is of order this 1 centimeter squared per gram. And said another way, this is literally, in sort of particle physics of order, a barn per 100 barn per MeV. Okay, so this is exactly the size of sort of strong scale interactions. Yeah?
So thinking about something like the bullet cluster, why would 3-to-2 be okay, but 2-to-2 be so problematic?
Well, the 3-to-2, okay, so 3-to-2 in general, we're having the 3-to-2 control my Rayleigh abundance, right? 3-to-2 is a process that is much more, 3-to-2 is frozen out, right? And what is the meaning of the fact that it's frozen out? It means it's literally rarely happening over here. Okay, that's very different from a 2-to-2, which in principle could still be active at a rate that's faster than that 3-to-2 process. And given that it's active, you can just ask, well, I have to make sure that I'm not violating limits that I'm seeing. Okay, so that's the exercise that I want to play here. Okay, so just taking this. So as I said, the reason that I'm mentioning this explicitly here is that certainly in the context of SIMPs, you'd expect that if I have strong 3-to-2 theories that have strong 3-to-2 interactions, I'll also generically have strong 2-to-2 interactions, self-interactions of dark matter, okay? Possibly exactly in that size of something that it's like a prediction of your theory as opposed to something you're inventing in order to solve a puzzle, okay? So just to give you sort of an example of what this looks like, so in the context of this Lagrangian, I can write down like our Lagrangian of our QCD theories. You can compute what is my self-scattering cross-section. Here's what it looks like. M pi n squared over 32 pi squared f pi to the 4th. And again, some combinatorical factor. I'll call it a squared over n pi squared. Okay, so this is combinatorics, some function of the number of flavors. And so now I take this and I require that it's smaller than my limit. And then going back to this picture over here, let's draw it like this. So here's my mass of my pion, and here's m pi over f pi, right? And here was my solution to my Boltzmann equation, okay? Which topped me off at some dark matter mass, roughly, say, of order a GeV. It doesn't even matter right now, okay? And now what I can do is along my solution to the Boltzmann equation, where for any m pi, this ratio is fixed, voila, my self-scattering is also fixed, right? Combinatorics is fixed by the number of flavors in my theory. And that's it. Everything here is determined. And so what I can do is draw along the solution to the Boltzmann equation, what does my self-scattering look like? Okay, and that looks, let's say, something like this. Okay, so what I'm doing over here is showing you what is sigma over m. And I'm going to require that this is smaller than that bound, okay, along the solution to the Boltzmann equation. Okay, and so by requiring that it's smaller than this number, what this is giving me combined is some range of dark matter mass in which everything is working. Okay, so my self-scattering is giving me a lower limit on my dark matter. This is telling me where I have a viable range. And we work out the numbers for many of these different gauge groups, and what always seems to come out is that the mass of these dark pions is typically of order a few hundreds of MeV. Yeah.
I think I just missed this, but how do you get that viable range?
How do I get what?
The viable range.
So along my solution to the Boltzmann equation, okay, m pi over f pi is fixed. So my self-scattering cross-section is fixed. So I can just plot, think of this as like another axis, the pink axis, okay? Values over here, okay, of sigma over m. And this is what that curve looks like. And then I require that that is smaller than 1 centimeter squared per gram. So as a function of dark matter mass, that tells me a lower limit on the dark matter mass. Okay, so now combined, I have a viable range for dark matter. Okay? Okay. Any questions on this before?
Boundaries under the assumption 100% of the matter is one component.
I don't have to assume that everything is one component. I do. So in fact, in these constructions, if you work through, for instance, if you look at that at our Witten term that sits over here, the statement that I kept saying about that I have to have that there's some topological condition, I literally need to have at least 5 pions. Okay, and so the minimal version I could do for this is an sp2 gauge theory in which I exactly have 5 pions. So I need all of these pions because we've written down a degenerate mass for the quarks. I actually also have a degenerate mass for my pions. So they're all active. I have 5 different pions, but they're all active at the same time. You can start playing games. For instance, if, as I said, I can gauge a subgroup of my residual symmetry to get my U1 dark, in which case I start having some charged pions, and I have to make sure that my mass splitting is such that enough pions can participate at the time of freeze out. The assumption is that at the end of the day, everything has cascaded down to my lightest state, if indeed not everything was stable. And then that at late times, when I'm talking about these self-scatterings, that's something that's happening now, not something that happened in the early universe necessarily, that over there, you take into account which pions you have. And in fact, whether you have your symmetry, your residual symmetry is broken or not broken, turns off some of the pieces that feed into the self-interactions. And that can also affect how broad or narrow your range is. Okay? Yeah?
To not overproduce dark matter, am I not in a small triangle below the purple and below the white?
Over here?
No, the triangle to the left of that.
Over here?
Yeah, right.
No, I mean, all I'm saying, think of this is like a different one. The white plot is giving me an upper limit, and I have a separate pink plot, which is along that curve. So any point over here, this is a point that's along this curve, but it's like my inability to draw too many dimensions on a 2D board. Okay? Okay. Lastly, I'll just add that there's, of course, another bajillion constraints that one could think about doing in general about dark matter. A big category of those is indirect detection. You're going to have a whole course on that next week. Okay? But the final type of constraint or possibility for detection that I want to talk about is direct detection. So I have around half an hour for this, which is more than I was expecting, so I'm very excited right now. Okay, so our next topic, or our next sort of category of constraints or possibilities for signals is direct detection. Okay, and now you have likely heard. Has anybody here never heard of direct detection? Okay, as one could have assumed, but basically the idea for direct detection is that we take. We assume that dark matter, or we want to ask ourselves what happens if dark matter interacts with some target that's sitting in the laboratory. Okay? So the idea here is that we're going to have dark matter, or search for dark matter, that interacts with some target that's sitting in a lab. This lab is, of course, typically deep underground. Okay? So the idea is that I'm going to have dark matter come in, okay, interact with my target. So again, time always flows from left to right. Okay, here's my dark matter. And let's say it scatters out. Okay? And again, I don't even care so much about how this interaction is happening. Very often, if you look at things in the literature, it's usually sort of drawn as if assume that I have some mediator that's mediating this interaction. Okay? But basically, the general picture is I have some target. And here's my dark matter. And it comes in. And the final state is who knows. Okay? This target gets, I don't know, it gets excited. Okay? Maybe it's going to shoot out a photon. Maybe it's going to shoot out an electron. Maybe it's going to shoot out a phonon. Something's going to happen to this target. And we want to be able to measure if and when something happened. Okay? And so we do have, of course, many experiments that are searching in this way for dark matter. Okay? So just sort of not going to do a full laundry list, but the Xenon 1-ton collaboration, Panda X, Crest. The list goes really, really on and on and on. Many, many experiments that are searching in this way. And here's what a typical plot from these experiments usually looks like. Of course, we have yet to detect dark matter, and so what we do currently is we place limits. And let's just take a look at what this plot usually looks like. So very often the plot, so I have over here some cross-section of dark matter. It's typically drawn between dark matter and nuclei, and it's usually a spin-independent, for instance, cross-section, okay, as a function of dark matter mass. And what happens is that all of these each experiment will place its own curve, but there's some curve that excludes regions of parameter space, okay? And just to understand what sort of the features of these curves are, and let's say the best, I don't know, right now, like the best limits are probably happening at around 10 GeV of mass. And this value over here is maybe 10 to the minus 46 centimeters squared. What's really controlling the shape over here is the following. So the turn up over here of where I lose sensitivity, this is sort of a combination of target properties, but also of thresholds. Okay, so target and threshold. And what's dominating this sort of curve over here is just the fact that, well, let's get to this in a second. Well, it's the fact that I just care about the flux of the dark matter that's coming in. So it's literally proportional to the energy density of dark matter over its mass. So you get this sort of, this type of behavior over here. But what is the rate that you would expect when you're scattering in this sort? The rate has the following form. Okay, so the rate goes like 1 over the density of your target. And then you have a piece that cares about the dark matter flux. Okay? You have a piece that cares about target properties. And then you have a piece that cares really about where the particle physics sits, which is that interaction cross-section. Okay? And just to mention over here, what is my dark matter flux? So my dark matter flux, would be the number density of dark matter times its velocity. So number density is this rho over m. That's why it's behaving in this way over here. And usually for velocity, what we do is we have some velocity dispersion. So there's really some integral over velocity with some distribution, what's called a standard halo model. Not going to be important for our purposes, so I'm not going to go into that. Okay? But roughly, this is sort of the structure of how a rate in a particular target goes. Tell me what type of interaction you want to talk about. And given the amount of events that they observe or do not observe, and the particulars of their target and their threshold, I can tell you what is their exclusion limit. Okay? Yeah?
I would assume the rate goes as a proportion to the target density.
What's that?
I would think the rate would go as proportional to the target density.
Well, so this is rate in this is number of events per unit time per unit exposure. So if you think about given a certain size of exposure and a certain target mass, it definitely scales. The rate scales with it. But this is like normalized to in units of mass time. Okay. And now what I just want to point out is what are these experiments typically looking for? Okay. What these experiments are typically looking for are nuclear recoil signals. Okay, so they're typically looking for nuclear recoils. Okay, so the idea is, I have dark matter that's coming in and scattering out. I have some energy that's deposited into the system, maybe with some momentum transfer as well. And here's my target at the beginning, target at the end. And the energy that's deposited in a nuclear recoil goes like the momentum transfer squared over twice the target mass. Momentum transfer is roughly the mass of the dark matter times its velocity. Okay? And when you plug in numbers, what you roughly get is this scales like EV, mass of dark matter over 100 MeV squared, and let's say a 20 GeV target mass. And so if I'm looking for a nuclear recoil signal and I want to be able to detect that something has happened, of course, this energy better be above my experimental thresholds. Okay, so I always want to require that to be above my experimental thresholds, and these are typically of order keV. Okay, and so if you plug in numbers, if you wanted to talk about a weak scale particle, which was really what motivated these types of experiments, these ginormous experiments that are really amazing. Let's say if you wanted a 30 GeV type of particle, your nuclear recoil energy is around 2 keV. You're a very happy human being because you can, in principle, either detect this or be able to say something about the fact that you have not seen it. But for instance, if I want to go to masses that are sub GeV, okay, to these lighter dark matter candidates, which as we've seen are completely non-exotic, they're completely generic. There's absolutely nothing wrong with dark matter not being at the weak scale. This is not such a great construction, okay? Not great for sub GeV masses. But you can really just understand everything in terms of billiard balls. Okay? So let's just understand what happens here in terms of billiard balls. So if I'm a heavy dark matter candidate, like a WIMP, which people were building these, people designed these experiments to search for, then it makes total sense, right? I'm a heavy dark matter, so I'm kind of like a big ball, okay? And if what I have sitting in my lab is another big ball, a heavy nuclei, okay, then it makes perfect sense. And a big ball is going to come in, it's going to be able to kick the big ball that I can observe in my lab, give it a kick, and I'm going to measure it, okay? So from the billiard ball perspective, this makes perfect sense. Okay, so you think of a WIMP as a large ball. Here it is, it comes in, I give a kick to that nuclei, and I can observe this kick, and I'm a happy human being, okay? This is very much not the case for the lighter dark matter. Because for a lighter dark matter, the kinematics is more like a tiny little ping pong ball that's trying to give a kick to a big bowling ball. Okay, it's just not going to work. That little thing just can't give a big enough punch to kick the heavy nuclei. Okay, and this is really why these experiments are failing. This is why we lose sensitivity in all of these different experiments when the mass of the dark matter roughly drops beneath the GeV scale. Okay, it's literally just billiard balls. So for lighter dark matter, which as we saw are very generic in theory land, this is just kinematically not going to work. Okay, so this is a ping pong ball that's trying to give a kick to a big bowling ball. And so if we want to be able to be sensitive to all of these types of dark matter candidates that are living in the sub-GeV range, this light dark matter regime, Does anybody have an idea what I can potentially swap out my nuclei for? Something small, right? All I need is something small, something light. And electrons are certainly a great way to do this trick, okay? Because if I ask you, what kind of materials have electrons in them?
Everything.
There's literally bajillions of materials that have electrons in them, okay? And they're each going to have their own strengths and their own interesting prospects. And we're going to sort of figure out together right now how to sort of think and organize our thoughts on this, okay? So yeah, it's much smarter to scatter off of electrons. And this basic idea is really what sits at the core. Sits at the core of all, or almost all, of the new ideas that are emerging over the last 5 to 10 years in the context of direct detection of dark matter, okay? This very simple picture that you guys were able to also identify just by thinking of billiard balls. Okay, so this is the basic idea. It sits at the core of the novel concepts in the literature. So to kind of organize your thoughts on the topic, let me provide you with the following energy guideline. Excuse me. So let's think of the following energy guideline. Okay. So let's imagine that we're talking about dark matter that comes and scatters with our target, okay? So if dark matter comes and scatters with the target, then what's the maximal energy it could possibly deposit into the system? It's coming in and it's coming out. The maximum it could possibly give a system is all of the kinetic energy that it's carrying, right? That's literally all it has to give in a scattering event. And so the maximum deposited energy would be its entire kinetic energy. Okay, kinetic energy, of course, scales like the mass of dark matter times velocity squared. Velocity, I remind you, ballpark 10 to the minus 3 in units of the speed of light. And so this is roughly a factor of 10 to the minus 6 times its mass. Okay? And so what this tells me is that if I'm thinking of the mass of the dark matter, and I want to construct some system that's sensitive to GeV masses, well, then I better find some system that in terms of the energy deposit that it's sensitive to, for GeV, I need 10 to the minus 6 below, and KeV energies, okay? And this is exactly what we're sort of kinematically matched for doing for dark matter all the way down to the GeV. But let's say we want to be greedy, and we want to go down to the MEV scale, okay? 3 orders of magnitude lower. Now I need systems that are sensitive to really small energy deposits of order in EV. And if I wanted to be even more greedy and go all the way down to that warm dark matter limit at a KeV, now I need systems that are sensitive to really, really tiny energy deposits of milli-electron volts. Okay? But this is really sort of the energy guideline. And we can really organize, I think it's over here. We can organize all of the existing ideas in the literature completely just based on the size of that energy deposit. Okay, so all I've done over here is to save us some time for me writing down all of these different types of experiments. Just take this energy deposit, write it over here. And here are lots of examples of categories of materials that people have already proposed in the literature for being sensitive, either for this sort of EV and above energy deposits. And we'll talk about a few of these examples: atomic ionizations, semiconductors, scintillators, two-dimensional targets like graphene, as well as others. And we now also have a lot of examples, or several examples, that are able to push down even to the milli-EV scale. Okay, so superconductors, Dirac materials, heavy fermion systems. And as you see, some of these involve, as we've worked out together here, interactions with electrons. Some of them actually involved in a smart way interactions with nuclei, where what you're looking for is not a nuclear recoil, but actually producing phonons. And for that, you can think of using color centers, superfluid helium, or polar crystals. Okay? And this is by no means mean to be, a complete laundry list of what exists in the literature, B, some statement as if these are all the things that one could do. Okay? This just goes to show you how with a very, very simple understanding of what's going on, and now you just think with an open mind, there's a lot that we can do. Okay? So what I'd like to do is kind of walk you through just a few of these examples to give you a little bit of a sense of how this works. Yeah?
Can we get around this velocity suppression in a similar way to the trick that was discussed earlier, where you just boost whatever nuclei or electrons relative to dark matter?
Well, so the way that I've described it to you right now is assuming I'm just talking about my standard halo dark matter. I could have some component that's perhaps boosted by all sorts of different ways, in which case I can ask, what is the type of constraint? How could existing experiments or other proposals be impacted by, if I had a boosted component, what could I say about this dark matter? And that's also a very active field of research.
But I guess what I mean is boosting the standard model particles.
It's not out of the question that one could do that. It's kind of difficult. We're going to talk about these types of materials, to think of how somebody would take, would take their semiconductor and boost it enough in a way that you'd be able to sort of to do something with that. But that's not saying that one day somebody won't be able to do that. Okay. So as we, so what I want to do now is sort of walk through a few of these examples to give you kind of a sense of the types of materials that people are talking about, the type of detection philosophies, the types of different methods and processes that you could think of to sort of open your mind in this direction. Okay? So before walking through a few of these examples, let me just give you two side notes, because you'll probably see this if you look in the literature. Do two side notes, and then we'll see how much of the examples we managed to get through before our time is up. Let's just do here side note 1. So side note 1 is that I probably don't have the rate written anymore over here, but I remind you that my rate was proportional, amongst other things, to my interaction cross-section, right? The interaction cross-section between the dark matter and my target. And so this is typically, just something you'll see in the literature, this is typically written as some reference cross-section. Okay, so it'll usually look like what's it called sigma E if we're talking about, let's say, we're talking about interactions now with electrons. And usually have a bar on top. Okay, so the bar will tell you it's a reference cross-section, where basically you're writing your real cross-section as some reference cross-section which no longer has momentum dependence, times something that's called a form factor. Okay, so it's usually capital F dm squared. Okay, so this is sort of something that no longer carries your momentum dependence, and this is something that carries all of the momentum dependence. And then people talk about, you can think of what is that interaction? Is it something that's mediated by a heavy mediator? Is it mediated by a light mediator? What does that mean in terms of what this form factor looks like? But this is sort of the heavy and the light cases. Heavy and light mediators are sort of the standard two that you'll always see appearing in papers. Sometimes there are also other types of interactions like EDMs and things like that one can, like dipole moments that one can think of writing. But this is just in terms of like how to read sort of the literature. Okay, so this has all of the momentum dependence. And this will usually include some reference momenta, which by convention is often taken as alpha times ME, okay, for historical reasons. So that's one side note. And then just a second side note about how one goes ahead to actually compute these things. So the other thing that we saw when we talked about the rate is that the rate is also proportional to target properties. Now, how do you compute these target properties that are relevant? So sort of historically, the way that people have always done this has been sort of looking at the overlap of single particle wave functions in the material. Okay, so I have some material. I ask what's my initial wave function of the initial electron that I'm talking with, and what's the final state electron, and then I do an overlap. And things get very messy very quickly. But there are things also get very non-exact very quickly, because materials are not, materials also have a lot of many-body effects that, that sit in them. And so we've kind of been able recently to develop a new way, new formalism in which to compute these types of things, which is more general. So let me just say this. So historically, you look at single particle excitations, and then you sort of do wave function overlaps between initial and final state. And what we've recently been able to understand is that you could actually do this in a much smarter way. It's typically faster. It's more exact. It encompasses all of the many-body effects of the system. And importantly, it's something that you can go ahead and measure. Okay, so you can literally calibrate everything based on real data. And the idea is basically that, if you think of a material, what is the response of a material to like an electromagnetic probe or to any probe? Something that people understand very well. This is literally the dielectric function that we've all learned in condensed matter 101. Okay, so we've developed this way to use the dielectric function, which is just the response of the system, or related to this is to use what's called the loss function, which is just related to this dielectric function. Okay, so it's just the imaginary of -1 over the dielectric function, which is a function of both energy and momenta. Okay? And it's literally just the statement that if dark matter comes in, my material properties are all determined, and somebody's already either computed this for me accurately or measured this for me accurately. Okay? So I don't have to reinvent the wheel, and I can actually do a much better job by using this type of idea. I'll just give you a reference for this. I know there are a few of them, but I'll just give you, this was a PRL we put out around a year and a half ago, 2101.08263. And there are a couple of other references that have appeared since then that you can follow up from there. Okay, so these are just 2 side notes that I think are important. And now I'll just mention a couple of examples of these materials. And I'm unlikely to be able to do as much as I've been hoping for. That's okay. Okay, so let me start with example number 1, which is also the first example that people thought of around a decade ago. There was a set of theorists who proposed that, if I want to look at these interactions with electrons to be sensitive to light-dark matter, then maybe I can, first idea, maybe I can use these big nuclei that people are already constructing experiments with and look at atomic ionization. Okay, so this is just, sorry, hold on. This is example number 1. Okay, so example number 1 are the first ideas. That were proposed in the literature. And the first one is to either look at atomic ionization. Okay, so have dark matter come in, deposit enough energy to ionize an atom. Okay, for instance, a xenon atom, and we have lots of data from xenon experiments. Or maybe dark matter would come in and excite an electron within a semiconductor. Okay, so maybe I have some valence band and some conduction band, and I deposit enough energy to excite an electron from down here all the way to up here. Okay. And so if you just sort of think of the energies over here, the energy to these typical band gaps of semiconductors are order EV. For atomic ionization, also the energies are typically of order 10-ish EV in most materials to ionize them. And so based on the energy guideline that we talked about, this tells you I should be able to probe dark matter masses all the way down to, we said, 6 orders of magnitude above the energy deposit, so MeV scale. Okay? And this is wonderful, and roughly now we're a decade past the point where theorists had originally proposed these ideas. And these ideas are being experimentally realized these days. So I'm sure you guys have heard of super CDMS. And you've possibly also heard of Sensei, also another awesome experiment. These guys are currently producing results using silicon semiconductors, very different technologies, very different detection philosophies, but already producing meaningful results that are placing limits on this sub-GeV mass range for dark matter. Okay? Silicon, as I said, by no means the only semiconductor you could do for this. You could use germanium, you could use diamond, you can use lots of other interesting stuff. It happens to be, we know to do a lot of things with silicon, and people already have a lot of detectors using silicon, so results are imminent. And also in the atomic ionization, xenon, 1-ton, n-ton, panda X, etc. We also have a lot of xenon information we can use to set limits currently on dark matter in this mass range. But I can only go down to MeV, right? So what happens if I want to go even lower? That's something I fundamentally can't do with the electronic excitations in these systems because of the threshold that they have. And so if I want to go lower, in comes example number 2, which is superconductors. So example number 2. superconductors. Okay, so in superconductors, what happens is that the ground state of the system is no longer free electrons, but it's energetically favorable for them to follow the buddy system. Okay, so they pair up in these pairs that are called Cooper pairs, and the binding energy of these pairs, which is the same as the gap of the system, is of order millielectron volts. Okay, so it's exactly in that right ballpark to be able to be sensitive down to keV masses. Okay, and when we first put this paper out with this idea, we'd kind of been thinking to do something very similar to what Super CDMS do in terms of their philosophy for detection. It's something called excitation concentration, where you kind of like, you take, let's say, a cube of, let's say, superconducting aluminum, and that's going to be your target. Dark matter is going to come in, create excitations, ricochet around, break Cooper pairs, and we can somehow collect and detect those excitations. But I'll just mention, actually, we're already able to set interesting limits in using a different philosophy, which I'll call the target plus sensor philosophy. Okay, so you can read about this more in, actually, I also have a more recent paper, but I'll just mention this original one, 1903, 05, 101. Where here the idea is, lots of people have superconducting detectors. And they have superconducting detectors not even necessarily for particle physics, okay? And so, for instance, we took a technology. It's actually developed at NIST down the road over here. They're called superconducting nanowire single photon detectors, a very, very long name. In short, it's SNSPDs. And the idea is, let me take this, even if it's a very, very tiny little target, okay? And in this case, it's really, really tiny. Here's what this nanowire looks like. It's like this. It's something, I don't know, it's roughly like 400 microns squared, okay? Something really, really tiny. And let me assume that this thing, it's not just, I cannot just think of it as the sensor that's going to notice something happen, but it can also literally be the target with which dark matter is interacting. Okay, so I take my tiny little device. Dark matter might come in, deposit enough energy to sort of activate it, okay, because it's a superconductor. And once it's activated, I'll be able to read it out, okay? And so using a tiny little device that just had 4 nanograms of material, okay, and using 3 hours of looking at it, we were already able to place world-leading limits on sub-GeV masses of dark matter. Okay, that really shows you the power of, if you can think of some new interesting material, some new interesting technology, even if all you have is something super-duper tiny, sometimes that's enough to be very, very powerful. Okay? This is by no means the only technology you can think to doing this with. At the time, we were working with a device that would had a 0.8 EV threshold, so nowhere near the milli-EV regime, and we were already able to say something very, very powerful. And these types of devices have already actually had demonstrated 125 milli-EV energy threshold. Okay, so there's a lot more that these technologies can be pushed down to. Okay, I was going to give you guys a third example, which I think I'm going to unfortunately have to skip. A third example, I'll just mention over here, was to use 2-dimensional targets. And this is something that in principle gives us the ability to do directional detection. So I'm happy to talk afterwards with anybody who's interested about any of these things, give you guys lots of references. I wanted to at least give you a little bit of a sense of the vast amount of diverse ideas that are existing right now in the literature. And these are things that are really like, this is happening right now, okay? So this is a really great time to start thinking about these things, because almost any idea you'll think of, probably nobody's thought of it yet, okay? And so maybe just the last thing before I finish our time together, just want to point out that anytime somebody tells you that they have some awesome detector for dark matter, you can always go much further than we've just discussed, because you can always have 2 for the price of 1. So I just want to explain that, and then we'll be finished. Okay, so what I mean by this, okay, so you can always go further. Because remember, we talked about this relationship between the energy that's deposited and the mass that I can be sensitive through scattering events. Okay, but there's another thing that could happen, which is not that dark matter comes and scatters with my detector, but that it gets absorbed in my detector. Okay, so I could have dark matter come in, interact with my target. Something's happening to this target, but no dark matter is coming out. And in this case, the deposited energy is the entire mass of the dark matter. Okay, and so that means that if we were thinking of these sort of curves over here, what was my energy deposit versus my mass of dark matter through scattering, where we saw that, for KeV, we were at GeV. For EV energy deposits, we were at MeV masses. And over here, we were at KeV masses with millieV. So there was this factor of 10 to the minus 6 between them. What this tells me is that, what I'm constructing is an experiment that has certain energy sensitivity. Okay? And that tells me that through absorption, I'm also always sensitive with KeV scales to KeV masses, with EV energies to EV masses, and with millieV energies to millieV masses. Okay, so that means that if what I've constructed is this experiment that's sensitive somewhere over here, I always get 2 for the 2 mass ranges for the price of 1. Okay? And so anytime somebody tells you they have a new material, a new detector for dark matter, why don't you ask yourself, to remind yourself of this, okay? I can always go at least twice what's very often stated. And I think this is a point that's being more and more appreciated in the literature, but it's a good thing to take with you if you think of these things. Okay, so that's pretty much it for me. I just want to, I don't want to erase that. I'm just going to erase over here. I'm just going to say this has been super fun for me. We've been talking together about mechanisms for dark matter, models for dark matter, a little bit now about detection for dark matter. But if there's one thing that I hope you really take away from this, it's the ability for you to construct the next amazing idea for dark matter, whether it's a mechanism, a model, or a detection. And I'm really looking forward to hearing your awesome idea. And thanks so much for your time. Yeah.
Could you try your calculator?
Ooh, yes. Okay, side note. Somebody, wait, you know who you are? I can't see you right now. Somebody yesterday came up to me, told me after class, that one of the Z3 diagrams that I drew for you yesterday, it was yesterday, right? All the days are sort of merged in, is actually a crocodile diagram. So actually, I could have had a crocodile diagram in my first sim paper had I just decided to draw the diagram in the thing. It was like a big shocker. But yes, here's my closest attempt for the crocodile challenge. It was when we were doing, we had a paper that we wrote on an axion portal, on a way to use an axion-like particle to mediate interactions between these simp pions and ordinary matter. There was some point where I drew a diagram, and then my collaborator Eric told me, no, look, if you just change the legs, here's what it looks like. So here was the axion. Here were, in this case, electrons. Here were pions, 3 pions, pi, and another 2, because remember, here's my Wessel-Witten term. Okay, voila, crocodile. Okay, like non-legitimate pieces of, but this, yeah. So unfortunately, and I got really, really excited. But you guys see this vertex over here, the 3 pions. We had to choose a gauge group in which this one vanished because otherwise semi-annihilations were taking over, and it wasn't actually a simp. So sadly, this whole diagram equal to 0. And when diagrams equal 0, you don't typically put them in your manuscript. So that's where that story ended. But this crocodile challenge has now been submitted to my Les Douches notes as an appendix with this literal picture, including the fact that it's 0. And fingers crossed that they accept it for publication and gets to see the e-printed world for real. Okay.
All right. I think with that, let's bring it along.
Thanks so much, everyone.